Okay.
All right. Today we have Markus Sperling tell us about 3D mirror symmetry with one-form symmetries. Take it away.
Right, then thank you very much, Julius, for inviting me and introducing me. And thank you, everybody, for coming to this unusual time. I tried to use today's talk to speak about a project that I had recently together with Satoshi Iwata, who's in Fudan in Shanghai, and his previous student, Wang Hao, and Zheng Hao, who is now in Oxford. And the topic, as you can see, is 3D mirror symmetry and one-form symmetries. So let's recall 3D mirror symmetry, which probably needs no introduction here, but let me just be brief about it, is one of the very important IR dualities we know for 3D n equals 4 theories. And thanks to various works of, including Ami, we have a very nice brain construction for many of the examples. And by now, there's a host of 3D theories for which we know what is the 3D dual, or the 3D mirror dual. And those go dating back to the very early papers, and then we have the very present or omnipresent paper theories like T rho sigma and the TG theories. And in all of these examples, basically what we expect is that we have two theories which are IR dual to each other, means they are equivalent upon exchange certain quantities. And we know that some of these quantities are, for instance, the two asymmetry factors. The others are, of course, which have been extensively discussed in this meeting, the Higgs and the Coulomb branch. Then we know that the formation parameters. And we also know that the electric and vortex particles are exchanged, as well as some defect lines, which are the Wilson and the vortex lines. On the other hand, we know that recently there has been quite some excitement about some generalized or higher form symmetries for various types of supersymmetric quantum field theories. And for the context of 3D n equals 4, there's basically three things that we need to take care of. One is the standard thing that we have been discussing for quite some time now. There's the ordinary symmetries, or the nowadays called zero form global symmetries, for which we know in the 3D n equals 4 setup, we have two types. One is the, I call it flavour symmetry, the other one is the topological symmetry, or if you like, you can think about them as the isometries of the Higgs and the Coulomb branch. And we know both of them are quite different from each other. The flavour symmetry is, of course, if you have a Lagrangian description, manifest in the UV Lagrangian already. The topological symmetry is at most manifest in a maximal torus in the UV, and it can be enhanced in the IR, which is, of course, then the most exciting case in which you have some non-trip enhancement. Besides these symmetries, we also need to include this extension, which is now the one-form symmetries. And here I'm only going to talk about the theories which have discrete cyclic groups. And the way we basically go about it is that there's sort of a very nice construction principle, which tells you if you gauge an abelian zero or one form symmetry in 3 dimensions, you're going to get a theory with a dual abelian one or zero form symmetry. So if we apply this to a discrete zero form symmetry, we're going to end up with a discrete one form symmetry in the corresponding theory after gauging. And that's going to be the main construction principle. And as you already see in the zero form setup, we have sort of two types of symmetries. So we can also expect there are going to be two types of one form symmetries, simply because they can have two different origins. And lastly, there's of course a possibility that the zero form and one form symmetry, they talk to each other. So sometimes they just completely are decoupled as a product, but sometimes there's a chance that we have this extension, which is called the two-group structure, which has been addressed by various people in quite recent times. And this is, we're going to talk about this in a bit. Now, what is the motivation for the project that we had? It was basically a very simple question. We knew that in the examples we know from mirror symmetry, most of the examples, they have no one-form symmetry. So we basically wanted to know what happens on the mirror symmetry if we have a one-form symmetry present, or what is the 3D mirror of the theory with a one-form symmetry. And in order to answer this question, we use a variety of tools. Of course, for the ordinary symmetries or for the zero form symmetries, we can use the tools that we have been developing for the last couple of years. So here we have, of course, any kind of exact computation like Taylor series, supersymmetric index. Any of those will give you very definite and concrete answers. On the other hand, we can also use some, let's say, less computationally intensive but more visual techniques. For instance, you can take the Coulomb branch global symmetry. In many cases, you can just read out from the balance set of the nodes in the quiver, and then you use the arguments that have been developed over the last years to deduce what are the monopole generators. Or if you go to the flavour symmetry, you can of course just use the standard gauge event operators that you can construct out of the Lagrangian fields in order to read out what is the local symmetry. For the generalized symmetries, so one form and two group symmetries, there's a host of techniques that has been developed over the last couple of years, or very recently actually. And here we're going to use some rather physical perspective, which is we're going to use line defects and we're going to use the equivalence classes in order to get an understanding of what the corresponding symmetries are. And the plan for today is essentially that we're going to spend quite some time on abelian examples to get some intuition. And once we're happy with that, we're going to move on to non-abelian case or to non-abelian quiver theories, which of course, first we're going to start with the linear unitary quiver. And once we're comfortable with that, we can move on to D and C type examples. And let's get into it. As always, if there's any questions in between, let me know. Otherwise, I'm going to proceed with the abelian cases. So first starting point is the well-known abelian mirror pair, which is SQED, and the linear quiver with n-1 U1 gauge nodes and the flavor and the front and the back. We know the global symmetries are U1 and PSUN, and there's no higher symmetries. Now, in order to approach higher symmetries, I wanted to use lines or line defects and their equivalence classes. And this is also going to be a nice exercise just to see what happens in case we don't have a global symmetry. So this goes back to a nice argument that Lakshya presented and also was presented in another paper by Leo, Morris, and Chicago, which basically goes as follows. We consider equivalence classes of line defects. And then we first of all say that these two line defects are equivalent if there exists a local operator at their junction. And then you can just consider the set of these equivalence classes. And they, for the theories that are considered here, they form abelian finite groups. And then you might ask, so what is now the importance of this abelian finite group that I denote with gamma 1 hat? Well, it turns out that if you want to define the topological operator which measures the charge of the line defect, then if two line defects are equivalent, so there's a local operator in between, then they necessarily need to have the same charge. So that tells you that the set of equivalence classes actually tells you the set of allowed charges. And then the topological operators, they are then given by elements in the contradiction dual, which is this gamma 1. And hence, by definition, this gives you the one-form symmetry. So in other words, if all of the line defects are equivalent to each other, there's only one equivalence class and there's no one-form symmetry, right? But if you have equivalence classes, more than one, and then of course you have a one-form symmetry. And one of the prime examples is that line defects can end or they cannot end. Because if line defects can end on local operators, and you don't need anything else on the other side, then the other side can always be identified as an identity line defect, and then they're always going to be identity equivalent to the identity, and hence there's nothing. But if the line defect cannot end, then it's not going to be equivalent to the identity, and that's the indicating sign for one-form symmetry. Right, and then you can sort of extend the setup to more equivalence classes if you just keep adding more information. So one type of information that we haven't included yet is the zero-form symmetry or the flavor symmetry. So if you think about a flavor symmetry, that's basically given by the representation this Wilson transforms it, then we can have two representations. And then we say, okay, they're equivalent if there's an operator which transforms suitably, basically meaning it's in the conjugate of one representation and it's the representation that is given. And such equivalence classes then, by the same reasoning, form again a finite group. And this turns out to be again the contradiction dual of a certain group, which is very important for us because that is the group that defines what is precisely the global form of the zero-form symmetry. So if you say F is sort of the unique simply connected group that is given for given zero-form algebra, then this Z defines precisely what is the global symmetry group. And lastly, we combine two things together. So we take line defects and we refine with respect to the global symmetry. So we keep track of both, and then we again define equivalence classes, which gives us another group. And now that the whole point of the exercise is that all of these groups fit nicely together, and they tell us, first of all, what is the global structure of the zero-form symmetry? Secondly, they tell us what is the one-form symmetry. And thirdly, they tell us if there's going to be some non-trivial interaction between the zero-form and the one-form symmetry. And the non-trivial interaction is actually given when this sequence is not splitting. In other words, if the epsilon is really a non-trivial extension and not just a product of the one-form and the zero-form symmetry, or the center zero. And I'm going to show you an example in 2 slides. Now I just want to discuss what are the relevant lines that we need to consider for 3D n = 4. And here, the story is again very symmetric, because remember that we have 2 types of zero-form symmetries. Correspondingly, we have 2 types of one-form symmetries. Correspondingly, we also need 2 types of line defects, which are going to be exchanged on the mirror symmetry. And the corresponding objects are known to be the width line and the vortex lines. So the width lines, they might be more familiar. You can construct in various ways. The standard way is you use this path-ordered exponential of the gauge field in the representation that you want to define the width line in. Or equivalently, you can introduce a width line defect into the 3D theory by coupling the 3D theory to 1D supersymmetric quantum mechanics, which has some permanent degrees of freedom. Likewise, you can also have vortex lines, which are sort of, so the width line is electrically charged, the vortex line is non-magnetically charged, meaning it's similarly defined as a monopole by a co-character of the gauge group. And here, again, there's various ways of defining it, which are largely believed to be equivalent. One way is that you introduce them via some singular solutions of the BPS equations. And here, the kind of equations that you need to consider are what's known as generalized vortex equations, hence that the whole defect is called vortex line. Or again, you can also introduce them by coupling some 1D quantum mechanics to the 3D theory, and now you're going to have the Masonic degrees of freedom. And the quite beautiful point is that there's a very nice paper from Benjamin Afsel and Gomez from 2015, in which they give you a very nice brain construction for 3D n = 4 for the A-typing equivalence, which then sort of makes the way you include defects into the setup very systematic for the brain system. Also for abelian mirror symmetry, the setup of defect lines is quite nice, because on the one hand side you have sort of a statement of sort of trivial defects that you can introduce. These are essentially flavor width lines and gauge vortex lines which you can screen. On the other side, the more interesting ones are the gauge width lines and what's called the flavor vortex line. And in an abelian theory, it's actually the very nice feature is that all of the half BPS vortex lines are basically equivalent to some flavor width line. To some flavor vortex lines. So you really only need to consider flavor vortex lines for the abelian mirror symmetry. Now let me show you an example to give you some flavor of what we're talking about. So for SQD, you can think about introducing a Wilson line, and the Wilson line has some charge L, right? So that's the standard gauge charge, and the allowed Wilson lines are basically given by the integers. On the corresponding mirror, you can have the linear quiver, and now I'm going to introduce the vortex line by coupling it to this one-dimensional supersymmetric quantum mechanics, where here this black dot is now a 1D unitary gauge field. So with UL, L gives now the charge, and then you have these red fields here, which are basically chiral multiplets, which couple to the 3D, and then there's also coupling to one of the chirals in the n = 4 multiplet. And this setup you can read up very nicely from a brain system. The point to make here is that, again, the vortex lines here are again just, or the setup inner equivalent vortex lines is just parameterized by Z, because you basically just need to know how you couple it to the flavor symmetry. You can think about introducing you can think about coupling the quantum mechanics to various other gauge nodes here. But actually, as it turns out, many of them are just equivalent by something that's called hopping duality. Or basically, if you want to think about a brain system, you can just move a certain defect brain without creating any new physical brains. So that's sort of a very nice statement that although you have a very long quiver, most of the vortex lines that you can introduce are just given by a very simple setup like this. Correspondingly, if you think about the vortex line in the SQD setup, the sort of procedure is very similar. You take the n flavors that you had at the beginning, and you split them, first of all, in 2 sets. And then you couple the defect quantum mechanics to one of the sets, and then the corresponding gauge node. And again, you have sort of 2 things to do. First of all, you need to specify the splitting. And secondly, you need to specify the gauge group of the 1D system. And if you then figure out what is the set of inequivalent vortex lines, you're going to find out It's just given by Zn modulo the simultaneous shift. And what is this? This is nothing else than the co-character lattice of PSUN, which is precisely the zero-form closed symmetry of the flavor symmetry. Right? So that makes a very nice context to sort of the more formal way of introducing a vortex sign by introducing a co-character into the gauge or the flavor symmetry combination. And on the mirror side, what do we do? Is the splitting basically becomes manifest to moving to the gate to the kth node in the quiver, and then the rank here becomes the charge of the Wilson line. So that's again sort of how the mirror works. Right? Any questions about these defects so far? Okay. Then let's talk about this applied to SQED, and then we're gonna introduce our first theory with a one-form symmetry. So if you remember for SQED, we just want to see that the argument presented before now works out fine. So what do we need to do? We need to look at the Wilson lines, and we know there's for every charge we have a Wilson line, and any of these Wilson lines can be screened, which means nothing else than I can end it on a suitable polynomial in the UV Lagrangian field. So that would be x with the y's. And what does it mean? It can end. It means I have a Wilson line, I end it on a certain polynomial, and then the other side is basically identity. So that means that all the gauge Wilson lines can end. There's no one-form symmetry, as we already know. If we look at the flavor or the zero-form side of the game, then we know that again these x's or their polynomials, they transform in certain representation of SUN, but they are not admissible representation of the global structure. So that means basically that this line now generates the center symmetry, which we need to mod out, which is the Zn. And now if we combine both of them, well, we would get the sort of the central group, this E. But here again, it's sort of the same argument. So we see that although we could write it down, but it's a fairly trivial exercise. The one-form symmetry is trivial, and we're just going to have the center symmetry being Zn. Now, let's go to some more exciting things. Let's introduce some one-form symmetry. The way we do it is we wanted to gauge something, and here we gauge a subgroup of the topological symmetry. So we start from SQD with n hypers of charge 1. We gauge a subgroup of the topological symmetry. And then we know this gives you SQD back, but now the charge has been changed to Q. So there are various ways of thinking about this. Either you follow a very nice argument of Nopadal and Matteo. They just show that you can write on the index of SQD. You do the gauging very, very explicitly, and then you just get the index for the SQD with charge Q hypers. Or you think about that gauging a topological symmetry means ungauging the corresponding gauge symmetry, which here now means you would just remove the ZQ, so everything needs to be in multiples of Q. Now, just going through the exercise, how to see the symmetries. Now what has changed is that we still have the Wilson lines of various charges, but now all the hypers or all the fundamental fields in the game, they have charge modulo Q, right? So if you have a Wilson line which has a charge not a multiple of Q, then it cannot end on a polynomial that we can form out of the fundamental fields. So we have several non-trivial equivalence classes, and we see that the number of them is basically given by just labeling through how many charges we have plus the identity. So we generate a group CQ, which is precisely the expected one-form symmetry that we wanted to see. For the flavor symmetry, not much has changed in terms of just thinking about background flavor with lines, but now we can also think about combining the line defects together with the flavor symmetry. And then we see that the charge Q Wilson line now can end on, of course, the charge Q hyper or the corresponding chiral. But again, it would be equivalent to a flavor Wilson line in a representation which is not permitted in PSUN. But then again, if you take the nth tensor power of that thing, we're going to get the singlet representation, which is again allowed in PSUN. That tells us that now the charge 1 Wilson line generates the group ZQ times n if we take into account the gauge center and the zero-point symmetry center. So that nothing else means then we have now this sort of very nice sequence that fits together. And we know that the sequence splits whenever the GCD is 1. And whenever it's larger than 1, then we have a potential of 2 symmetry. So in particular, if you go back to the example that, for instance, Nopador and Matteo or Sakura, Matthew, and collaborators have been considering SQD with two hypers of just 2, then you know the GCD is 2. So you're going to have a potential to group symmetry. Right? So that's sort of the way to see this with alignments. Now, let's ask the question, what is a corresponding mirror? Well, the corresponding mirror is nothing else than you take the abelian mirror and you gauge the ZQ now in the flavor symmetry. So formally you can write down, it looks like the affine quiver. You have n-1 U1 nodes, and you have one node on the top, which is sort of a discrete gauge node, so a ZQ. So what happens to our lines in order to sort of foster this understanding is, remember before we had this statement, right? So the width lines here, they correspond to this vortex lines here. And before gauging, we know all of these charges are admissible. Now after gauging, we know already what happens here. We know we need to have the width lines which have mismatching charges, which are not multiples of Q, they cannot end, so they generate us the one-form symmetry. But here it's sort of the same game, because now we gauge something of the U1 flavor symmetry. And again, we gauge in ZQ. So now we know that the vortex lines, which have mismatching charge, they again cannot end and degenerate as the one-form symmetry. That's sort of a very nice picture following this. So here, but here sort of was a very nice or very simple example, because the symmetry in which we have performing the gauging is just a U1. Now, if we sort of turn around the logic, we can go.
Marcus?
Yes.
Can I just ask a question on the previous slide? Yeah. So here, can you still draw, like after gauging, can you still draw the black dot attached to the ZQ? Like this is how you would draw it. So you would take the quiver above and then attach the UL.
Maybe, maybe. I mean, in principle, you can write it and then just explain what you mean by it.
Okay, but so
right. I mean,
but it's what you're saying here. This is not what you're saying here.
Right. I would just I used this picture before gauging because that one is sort of very clean. You can even write it down with brains. This one, I would not necessarily write it down. I would just
the question is to explain what would be this red arrow between the ZQ and the UL, right?
That's right. That's why I'm sort of hesitant to write it down.
Okay, thank you.
In principle, you can also make this precise if you recall that here you take the you write down the co-character, so of U1 into U1, so it's the integers. And then here you sort of have to now do the same thing, but now U1 is mod ZQ. Right, and then you see that the thing can only end when it has a mod Q charge.
Yeah, sure.
Right, but this picture, not sure.
Okay, if you're not saying that you have this picture for after gauging.
That's correct.
Okay, thank you.
Right. Right. Now I want to turn around the logic. I want to, because sort of what is sort of nicer to do is sort of always, I like gauging on the topological symmetry and then go the other way around. So what I do now is I'm going to go to the abelian linear quiver, and I'm going to gauge again a subgroup of the topological symmetry. And I make it very nicely because I choose a U1 that sort of matches the U1 in the UV, or the topological symmetry of the gauge node in the UV description. And then what you get after gauging is sort of a very nice or straightforward generalization of the SQD picture. You just pick a node and you just increase the charges on this corresponding node. So you're going to have, instead of bifundamentals with charge 1 and -1, you're going to have a bifundamental with charge 1 and -Q and Q and -1 attached to this particular node. And then, of course, there are two questions. What happens with the global symmetry, and what is the corresponding mirror to this kind of theory? In terms of global symmetry, you can compute very explicitly that your PSCN is now given by this expression. So it's an SUK times U1 and SUN minus K. And you're going to have the center symmetries of the non-abelian factors acting. And they're not just acting on the non-abelian factor, but actually they also play around with the U1 in a way that we say that the ZK is generated by this combination. So you see it acts on the U1 depending on the charge that you have introduced, and the same way on the other way around. Now, this on the one hand side follows from just the computation. On the other way, you can also try to understand it by the usual graphical way of doing it. So you would look at this quiver. You would have two balanced sets. So you'd have the AK-1 Dinkin diagram, and you would have the AN-K-1 Dinkin diagram over here. So they give you, of course, your abelian factors, non-abelian factors that you expect. And then we need to understand how the unbalanced node is connected. So here we see the unbalanced node is connected to the last node. So that would be corresponding to the anti-fundamental representation, which would have charge K-1 under the center symmetry. But now you can convince yourself that since you changed the charge over here, there's also an increase in charge, because it's not just the anti-fundamental, but actually the anti-fundamental, the Q symmetric power there that appears as the representation for this corresponding monopole operator. So you see that the operator, the monopole operator, which has non-trivial topological charge here, would have center charge, which is given by Q times K-1 mod Q, which then turns out to be minus Q as given here. And the same exercise you can do on the other side. You would again look at this balanced set. You would look at which Dinkin node the corresponding U1 is attached to. So here the fundamental representation. So you know that one has charge 1, but then there's a modification because you change the charge over here. So you're going to have the Q symmetric of the fundamental representation appearing for the monopole charge under this topological symmetry. And then you get exactly the same conclusion as you would get from the explicit computation. Now, in terms of the mirror, you have to play the same game, but now it's a bit more complicated because you need to figure out which ZQ inside the flavor symmetry you need to gauge. And the way you're going to do it is that you use the mirror between the parameters of the SQD and its mirror. And then you need to remember.
Sorry. So the point here is that Gaiotto and Witten told us a long time ago how to compute the enhancement on the Coulomb branch at the level of the algebra. And the point there is to bump that up to understand the global form of the flavor set Coulomb branch.
That's right.
Yeah.
That's right. Yeah, I mean, so usually I think for a long time we have been saying, okay, there's a SUK, there's a U1, there's an SCM minus K, and then on the level of the algebra we're done. But if you keep track of the representation, you can also read off the center symmetries, right? I see. You would agree to this, or?
Yeah.
Very good. Very good. Right. Yes. So on the mirror, you need to figure out which ZQ to gauge, and you need to remember that in the mirror, what you have done is you have selected a topological cartan in the UV. So you first of all need to go into the IR basis for the cartan element. So you use the cartan matrix. And then you can read out how the ZQ is acting on the fundamental flavors. And it turns out, that you do a very similar thing. You split the flavors into two sets, and then you act on one of the sets with the ZQ, and the other set is unaffected. And if you follow this recipe, you can essentially, again, by some arguments, you can construct an operator, which is gauge invariant, which then precisely reproduces the charges that you would expect from the global symmetry. So the way you do it is you allow me this kind of funny notation. You have an X that belongs to this set of hypers, and you have X tilde to the set of hypers which is not affected. Now, in order to make it U1 gauge invariant, you need equal powers of X and X tilde. And in order to make it ZQ invariant, you need to have at least Q of those. So you see that this operator transforms under the non-abelian flavor symmetries like this. And then you have a U1 factor floating around. The U1 factor, basically, how to think about it is you can, first of all, assign a U1 factor for each of the two sets of flavors. Then you remove the diagonal U1. And then you have a leftover freedom to define how you choose the charge Q. And here the charge Q is chosen such that the operator O, which is the lowest operator charge under this additional U1, has charge 1. Right, and once you do it, you see that the non-abelian part has then given center symmetries under the ZQ times CM centers, and you see that you can compensate by embedding the ZQ times CM suitably in the U1. And if you do this, you precisely reproduce the symmetry that we have written up here. right? So that's the way how you can convince the set that it works nicely. Now, let's have a look on the defects. And again, I draw a picture before gauging because there everything is sort of okay. And after gauging, I just say some words, but sort of the spirit should be understood on with some caution. So before gauging, again, on the Abelian mirror, we have the width lines of any charge, and on the side.
Sorry to interrupt. May I ask you some question?
Yes.
Hi. This previous slide, sorry for this stupid question. I don't know if I understand. When you chiral notation, right? Or it's a chiral multiplet, right? Not it's non-simply laid.
Say again.
Sorry. I'm saying that when you use the arrow back and forth, these are chiral, right?
That's correct.
Not the non-simply lace, right? Like in the
that's
previous.
right. Yes. So this is the chiral thing, right? So I'm making a half PPS operator.
So two pairs there, just charge under ZQ, just a generator of the CQ, and then charge -1, right? That's how I should read the arrow, right?
Right. Yeah, that's the same thing, right? You have one of them charge 1, one of them charge -1.
Okay, so it's a normal. Okay, I see. And
yes,
the other
yes.
is just normal, just 2 copies, you mean?
Yeah, here, because I've written this K here, so it's K of them. So I couldn't draw K errors, so I just drew 2, and then I have a K.
K means you have a K copy of going on the right and K copy going on the left, right?
Exactly.
Okay.
So I take the N flavor, I split it into 2 sets, K and N minus K.
Yeah.
And then on the set of K, I act with the ZQ.
Okay, it's clear now. Okay, thank you.
Thank you.
So can I ask one more question on this?
Sure.
So your other quiver, the mirror to this, is completely symmetric in exchanging K and N minus K, right? It's just flipping the thing around. But your mirror doesn't seem to be symmetric. So what
it is indeed.
Of course, it has to be. But is there a way to draw it in a symmetric way?
I could draw the same picture, but I act with a ZQ on N minus K.
Right, but then it seems that you always need to, like you have short, and you have those with charge Q and those with charge 1, and it's never symmetric. It's,
Well, so there's sort of a little bit of freedom how you do a global U1 rotation. And that is precisely the way how you see that you can act with the ZQ on either set of them. Right, so you can act with the ZQ on the case on the set of K, or you can act with the ZQ on the set of N minus K, or if you like, you can also distribute it on all of them. That is also what you can do, but for some reasons I kind of prefer putting it on one set and not on the other. But in principle, you can. There's some freedom in assigning how the ZQ acts, simply because there's a U1 freedom.
Yeah. Okay. Yeah. Thank you.
Yeah, we're gonna see this sort of freedom later on again if we go to the TSVM things. Right. Right. So what happened with the lines? Just to wrap it up. So on the mirror side, we again had these width lines. If we gauge, this one has only charge Q hypers connecting. So we see that after gauging, the lines which have mismatching charge cannot end. And the same is sort of true for this defect here, because again, you can sort of think as an overall U1 being embedded here. And then you sort of gauge inside that U1. And then you see again that there's a corresponding mismatch if you gauge the D1 inside this box as sort of an argument to do it. Right. Let's see. So that was sort of what I planned for the abelian part to get started. Any questions about this before we go on to the TSVM part? Okay. If not, then let's get a warm-up on the non-abelian things and start with SQC. So here is the story is sort of the same exercise. We start from SQCD, which has a known symmetries, and then I want to gauge something in a topological symmetry. And here I need to be a bit more picky for reasons. The reason being that I want to have a nice theory after gauging, so something that I can sort of reasonably well write down. And what I do is I pick a cyclic group, which is an integer multiple of the center symmetry here. And that then leads to the following construction. You get an SUK gauge group, you get a U1 gauge group, you get n copies of the hypermultiplets in between. And now there's sort of an arrow. The arrow does not mean it's non-symmetry laced. The arrow just means that I increase the U1 charge to be A instead of 1. So the bifundamentals here, they're going to transform into fundamental of SUK, and the charge A representation of the U1. And then I have n of them.
How is that different from being non-symmetry laced in this case?
But for this one, I can write on a Lagrangian.
But if the
yeah, for U1 there's no difference. I just want to emphasize.
The long side is
yeah, for Lagrange, for U1 there's no difference.
Okay.
I just
so
want to
here
emphasize.
There is no difference between the two things. Okay, good.
I just want to make sure not to scare anyone. It's just it's just
I could treat it as non-symmetry laced.
You can treat it as non-symmetry laced.
Perfect.
Yeah, I just not to scare anyone. It's just a charge of the U1, so nothing fancy. But good question. Anyhow, so what happens now is we're going to PSUN flavor symmetry. We're going to have a one-form symmetry, which is given by ZQ, which is A times K.
Marcus, will you go and say that this is a Lagrangian for non-symmetry laced?
No. That's why I didn't say that.
But if there's U1 nodes, the non-symmetry laced is Lagrangian, right?
Right.
Was there ever any dispute?
What's the question?
If it's let's say the quiver just has U1 nodes, then the non-simply laced is Lagrangian. It's just the charge of the U1. It's when you have nodes of rank K that you get a problem. That you only take the weights of the fundamental representation and you shift them all. But for U1, it's still a representation.
I think there will be a problem with the heat sponge. Can you compute the heat sponge?
Of course. If it's just U1s, but okay, let's discuss later. But just the charge of U1, that's a representation, right?
Just to comment, there's definitely a Lagrangian because you can take super QCD and couple it to a TQFT. That's what you do when you gauge the thing. But I'm not sure that's a Lagrangian in the sense that you would wish it.
But here it's definitely perfectly Lagrangian.
Right.
Okay.
Right. Okay, so just before, so now my convention arrow with a little number next to it means just the charge of the U1 is increased. And we can go again through this argument with the lines just for fun. We can look at a suitable wisdom line, which is trivial in what happened now? Oh, sorry. Which is trivial in the SU factor and has a charge -1 in the U1. We can see straightforwardly this cannot end on anything because the charges of the hypers don't match. But again, you can sort of take the qth power of that thing, and that can end on the determinant operator. Well, basically, you take the epsilon symbol in the SU, you form the determinant, and then you can compute the charge of x. Charge of x is A. The determinant is k copies of this x, suitably antisymmetric contracted. So you get k times x, which is k times a, which is again q. So you know that this thing can end on a suitable operator, which then tells you that the one-form symmetry is now ZQ because you have q non-equivalent or non-trivial equivalence classes. Now, if we keep track of the zero-form symmetry, we want to basically find out what is sort of the interplay between the gauge center and the zero-form center. We know again that the fundamental flavor wisdom line is in a non-allowed representation of PSUN. So we see this group that we need to define the global symmetry is Zn, so the whole center. And then we see that the operator that we wanted, this determinant operator that we wanted to use, transforms in the case antisymmetric of the antifundamental, which generically is not in PSUN, right? So there needs to be quite a lot of coincidence in order for this to be of zero center charge. So what we need to do is we need to take the operator to the power of n, because then we are for sure that this contains a singlet. So we see that there's again this phenomenon that we have a line defect, which ends on a local operator, which is a non-allowed representation of the global symmetry. So that is an indicator for this sort of extension, which is then CQ times n. And we again see that there's a possible extension or non-trivial extension if the GCD is larger than 1. So that's sort of applying this logic to a non-abelian example. Just to complete the story, there's also something that you can also do. And instead of gauging something that is a multiple of the center, you can also gauge a subgroup of the center. So like a ZQ inside ZK. In principle, you get the same thing. You get SUK and D1 with the n hyper or n bifundamental hypermultiplets in between. And you sort of need to gauge a ZD subgroup of the corresponding potential one-form symmetry. What that basically means is that you need to extend the magnetic lattice in this sort of half-intershift fashion, as we have discussed in a paper with Antoine, Julius, Ami, Rudolf, and Zheng Hao back in 2020. You can do that, and it works out perfectly fine. I'm just not going to do it because it's a bit cumbersome to keep track of this non-funny lattice. If you do the other examples, you're always going to have a lattice which is an integer lattice, and everything is sort of easier to think about. Now let's go to TSVN. We know TSVN is sort of this very nice self-proof theory, and we know that all of the other T-row sigma theories come from TSVN just by some hexing. And the global symmetry is again PSUN in both factors. And we ask the same questions: what happens if we start gauging things? And again, I'm going to start with gauging on the topological symmetry. And again, I embed it suitably in UV topological Cartan factors. And you can now do the same exercises as before. You pick a UK, you pick the ZQ to be a multiple of the center symmetry. And then you get a description which is replacing the UK by SUK. You take the flavor altogether, you put a U1 there, and then you have n copies of them in the last node. And then depending whether A is 1 or not, you get some higher charge in the U1. Right? That's sort of a very nice description, and we sort of are very happy to see such a simple Quiver. Now the question is again, what's the global symmetry and what's the mirror? In terms of global symmetry, you again have two choices. You can take the topological symmetry and compute it honestly. You find, again, it's sort of a mix of three things. It's the SUK, SU1, and SUM minus K. In this particular example, you will see that the center of SUK does not interact with the U1, but the center of Cn minus K does interact with the U1 depending on the charge that you have gauged. And you can again read this up from the Quiver in sort of a nice fashion. You check the set of balanced nodes, which is again giving you SUK and SUM minus K, and then you check what is the unbalanced or where the unbalanced U1 node is connected to. And let me just show you again. So here you see that the U1, of course, is not connected to this thing here over here. So the corresponding monopole operator transforming non-trivially under this topological symmetry here is not going to interact with this one. So the simple symmetry does not act, but it does interact with this one. And again, it's correspondingly attached to the Dinker node of the anti-fundamental representation. So we know there is at least the charge of the anti-fundamental representation, which is n minus k minus 1. And then again, there's a modification because of the symmetry that you have gauged. And you can think about it in the following way. There's one sort of enhancement or sort of one contributing factor is the SUK node. And the other contributing factor is the same as in the U1 case. It is the increased charge of the U1, which again, both of them conspire to give you Q times the original charge. And then you get the same global symmetry as if you do the corresponding computation exactly. Right, so that's sort of a very nice feature for this linear Quivers. Of course, the one-form symmetry is by construction ZQ, and for the two-group symmetry or possible two-group symmetry, we sort of expect the same scenario as before, simply by the same arguments now, just a bit longer. In terms of the mirror, we see it also behaves very, very similarly to the U1 case. In a sense, there's only one flavor symmetry, and we again need to work out how the ZQ embeds but it's fairly the same exercise since there's only one flavor node. So you just need to remember, you started working in the UV carton, so you need to go back into the IR, use the carton matrix, and then you can find out what is the action of the ZQ on the flavors. And you can again find a very nice choice in the sense that you can split the flavors into two and only act with ZQ on one of these sets. So again, that means there's n minus k flavors here, and there's k hypers which are affected by the ZQ. And then you can convince yourself that using again the notation of Quiver multiplets here and constructing a gauging rate operator, that you can again explicitly can construct an operator which confirms the center charges in the U1, telling you how these charges work out. And again, these Qs here is basically you artificially introduce the U1 factor for each of these sets, you remove the diagonal U1, and then you use the overall freedom to define what is the U1 charge of this operator. And again, the operator is the first non-trivial operator charge under the symmetry. So I just define it to be of charge 1, and then you get the symmetry that we already have. That's simple. Right, so it's sort of a nice exercise. Now, before going to the other cases, let me just give you an example of what you can see for the corresponding mirror maps of the parameters. If you're interested in the UV parameters, you can very explicitly derive just a simple relation like this, that all of these topological factors here, they are given by ratios of the flavor symmetries. And the last one here is essentially given like some nth power of the last one. If you want to have some more manifest variables, so you introduce the symmetry fugacities for the SU k factor here and the SU m minus k factor here. So I call them x and u, and then you introduce a q factor here. Then you sort of have the usual transformation properties of using the Cartan matrix for the topological symmetries. And for the flavor symmetries, you have a corresponding expression very, very explicitly, which then tells you precisely how the mirror map between these parameters is realized. And this you can explicitly derive. So there's sort of no guesswork. You just start from the known mirror map, and then you do the gauging very explicitly, and you get kind of this result. There's one case which I sort of explicitly or implicitly didn't mention before, is I assumed in the previous page that basically the one or the UK node that you gauge on has k at least 2. And then the thing worked out very nicely that you do SUK and the U1 in the end. If you would start gauging the topological symmetry associated to the U1 in front, then it's more like the SQCD example that you would just increase the charge of the U1, and then everything works out nicely as before. Right, so it's sort of not an outlier, it's just like slightly different. Now let me comment on T over sigma before going to some nonlinear examples. So for T over sigma, you can sort of more do the same thing. Everything just becomes a bit more cumbersome. Again, you better choose the ZQ to be nice in order to get a simple Quiver description after the gauging. So again, you can choose one of the gauge nodes. You gauge precisely the Z and K, which belongs to the center, and then you get SU. And then the global symmetry you can work out straightforwardly. And on the mirror side, you do the same thing. You just identify which subgroup to gauge, and then you sort of have it in 2 sets. So let me demonstrate that on 2 examples, just to give you a flavor. So if you take like this example, some TSU15, you choose some partitions, and then you get a theory which has 2 U2 nodes. So we have chosen to put either of them to SU2. So if you chose the right one, then you would get a corresponding mirror, which you, for instance, you can choose the Z2 to be acting on these 2 hypers, or flavors, or you can choose the Z2 to be acting on these 3 hypers. And both of them give you equivalent results, that you find that there's a balance node here, there's 3 unbalanced nodes here, but then basically the center symmetry of this node is also acting on the corresponding topological symmetry here, simply because it is connected to it, and it's connected to the first Lincoln label, so it's the spin representation, which is non-trivially acted on by the Z2. So in the end of the day, you find there's a U2 times a U1 times a U1. Right? It's the same exercise. And if you would do it on the other side, you would get a different symmetry, because now the balanced node is not connected to any of the other unbalanced nodes, which gives you a topological symmetry. So you're just going to get a PSU2 times U1 factors. Right. So that's sort of the way it goes. But of course, the generic case is quite cumbersome. Now, after having done the A-type thing, now we can go to some more daunting exercise. We can do a D-type Quiver. Here, of course, there's certain things you can't do, and there's one thing you can still do. So on the for autosymmetric Quivers, we know there's sort of a shortage on topological symmetry that you can refine. So here we restrict ourselves to gauging the topological symmetry in the D-type Quiver and comparing it to the flavor symmetry on the autosymmetric mirror. But the logic is very much the same. So you have two choices. Either the SU node is in front of the flavor symmetry. Then you would get a global symmetry, which is has an SU factor, has a spin factor and a U1, and then the centers act. But the way the centers act, you can either deduce by computing it, or you can again just look at the Quiver. You see the balance set here for the SU is not interacting with the unbalanced U1. So the U1 is not going to be affected by the center symmetry of SU. The D-type one is going to be, or the center symmetry of the D-type Dinkin Quiver is going to interact with the U1 here, simply because it's going to be attached to some Dinkin label, and then it's basically the representation, its corresponding center charge that is going to be affected by the U1. And again, you could also gauge a different group. So you could gauge like an integer multiple of the center symmetry associated to SU, and then you would increase the charge of this U1 here, and then you would slightly modify this charge assignment here. So that works similar as in the A-type case. And if you do it the other way around, you would gauge topological symmetry associated to the node after the flavor. Then of course you would sort of flip it around. Now the U1 and the SU sort of are affected by the center of the SU node, and the D-type Dinkin Quiver, so there's no interaction of the U1 and the corresponding center symmetry of the D, and you would get this kind of symmetry. Right, that's sort of a very straightforward generalization of the A-type case. Something more daunting is a C-type Quiver or non-symmetry Quiver, which in the case of if you restrict to SQCD, is sort of pictorially the same thing. But now you have this non-symmetry laced edge that you need to take into account. So there's a slight thing that you need to work out, because previously, basically, what you do in terms of thinking about like an index or the Hilbert series is that you need to take the U node. So you take a UK and you want to gauge the topological symmetry associated there. Then basically what you can do is you can think about it writing UK into SUK times U1 mod the ZK. And then you sort of shift all the magnetic fluxes of the neighboring nodes by this U1. And if you do this carefully enough, and then in the end you gauge the right symmetry, then you get back the index or the monopole formula for the Quiver after gauging. Here, there's this non-symmetry laced factor or this non-symmetry laced edge, which then sort of spoils a little bit the game, and you need to be quite careful how you define the Quiver after gauging. So if you do it on the long node, it's sort of rather mild. So if you have the UM3 and you turn it into SUM3, and then you gauge the corresponding ZM3, then all the flavors they collide together into one gauge node. You're going to have these multiplicities of these hypermultiplets associated from here, and you need to increase the U1 charge of the sort of flavors on the short side. And then the magnetic lattice is still the integer lattice. But if you do it on the other side, if you would do it on the short side, you sort of still would do the same thing. All the flavors collide, and you need to adjust the U1 charge of the previously flavors on the short side, but you also need to change the lattice that you need to sum over. And once you do that, you produce consistent results with if you do the gauging directly. So if you do it for the C-type Quivers, like for the simplest ones, then you sort of can go through different nodes, and you get precisely some symmetry breaking, which is consistent with if you do it big before, right? So that's sort of a slight issue that you have to be more careful about the lattice that you're going to do. But that's sort of the only kind of complication you need to worry about. So now let me summarize. So basically, the question that we had is what's the mirror of the 3D theory, the one-form symmetry? And the way we went about it is that it's sort of this very nice and very systematic way of doing it. You can generate one-form symmetries simply by gauging a billion zero-form symmetries. And here we are sort of restricted to the theories which have a simple Quiver description. So we always started from the topological symmetry, we gauged it suitably, and then we used the mirror map of the non-mirror map before in order to derive what is the actual of the discrete group on the corresponding mirror. And then we have verified the symmetry patterns match and indeed verified the global structure. And for the non-simplest ones, we sort of propose what happens if you do on the long and on the short side with a single SUN node. There's certain topics which I didn't discuss today. One of them is autosymplectic quivers in further detail. One thing is that, of course, the topological symmetry is sort of absent or famously absent. But what you can do is you sort of can look at the special orthogonal nodes, which do allow you to introduce a Z2. You can always gauge that Z2, which sort of has the immediate effect that you turn the SO node into a spin node. And correspondingly on the mirror side, you sort of do the same kind of exercise. You would split a corresponding flavor and act with a Z2. That's sort of a thing you can do, but I didn't want to complicate things too much. And of course, all of these generalized global symmetries, you can ask what is the corresponding anomalies between them. That's something that various people in the audience have worked on, so I didn't include it too much. And with this, if there's any further questions, please let me know. Otherwise, I thank you for your attention.
All right, let's thank Marcus. Questions? Okay, apparently you were very clear.
I see. Good.
Okay, Antoine agrees. He gave the thumbs up.
Very
That's
good.
good.
Very good. Very good.
Yeah, I also have no questions. It was very clear.
Oh, very good. Happy to hear it.
What's next?
A couple of things.
So
like
actually, I do have a question, and it's of course the first question that we should ask is there any relation to brains?
Good question.
Can we if we think of discrete gauging in brain systems, then of course there are constructions to do this in some cases. Can we implement them here? It's crazy. But okay.
Good question. I thought about it for a bit, but no, not sure.
Okay.
Not sure.
Okay.
Well, you can also ask you could also ask like for the magnetic quivers, for the ones that it's the same question we had in 2020, right? If you have the magnetic quivers, why do you have to remove the one symmetry?
Yeah, so this is why I ask, because for magnetic quivers, for example, or in general, whenever we read a quiver which we can interpret as a 3D n equals 4 quiver, it never has a one-form symmetry if it's read from a brain system. This is kind of the what I take away. So is there a brain system where you associate a magnetic quiver or a 3D electric quiver where there is such a thing?
Yeah,
I guess there can be some accidental cases, but in general,
yeah,
I don't know. Okay, anyway.
Yeah,
good. So there are things left to do.
Would be yeah. Well,
I mean, you want to understand how to do discrete gauging, right? At the level of brain.
Sure. Yeah. Exactly. So we have orientive folds or S folds that we can use to do that, but yeah. Like the theories that Marcus showed us right now, we don't see. Nor also, let's say if we read an unframed autosymplectic quiver from a brain system, then it turns out that the one-form symmetry, the set 2 center one-form symmetry, should actually be gauged. So yeah. And so since Matt is here, did you think about stacky Higgs branches, Marcus?
I asked Matthew a lot of questions about that when he gave a talk.
Okay. I see. Very good.
But otherwise, no, I still have to digest the higher category things that matter, or higher representations. That yeah, this one I haven't. I mean, as far as I understand, Matt, then all of these line operators, or all of these lines is basically you can also think about it in terms of his stack construction, but.
Yeah, like you want to think about the Wilson lines as like line bundles on the Higgs branch stack, and then the fact that some of those Wilson lines can't end kind of reflects the fact that they're fractional line bundles.
That sounds very cool.
But I mean, yeah, but the stacky thing is not. It's not a kind of, it's not a technicality, right? It's encoding something very physical.
Yeah.
Which is the point that if you move out to a point on the Higgs branch and you look at what the theory looks like at low energies, it contains a TQFT. It has a discrete broken gauge symmetry, and it's some geometric thing that captures that.
Okay, good. Do we have more questions for Marcus? Maybe people came up with some.
Have you thought about gauging? I mean, one thing you can try to do is to gauge discrete symmetries that are not of the type you discussed, but are more like outer automorphisms of the gauge group. So there might be an outer automorphism of a gauge group at a single node, or it might come from an automorphism of the quiver, because I think these things are very different, and they will lead to non-invertible symmetries typically.
Like SU tilde.
For example, yeah.
I see. I haven't.
Or if you gauge, if you have a spin node or something like that, and you gauge the center. Sorry, if you gauge the outer automorphism, the Z charge conjugation, Z2, you're going to get like.
You want to make it pin.
Yeah.
Right.
Yeah, those things will have, assuming it's not broken by the matter, those things may have non-invertible symmetries.
You know that Nobedon has some of these in his paper with Matteo. Like he considers some of those.
Yes.
Right.
We do that invoke to go from SO to O, for example. This is invoke charge conjugation, but this depends on an anomaly polynomial, and then this is known from Kaidi, Omori, and Zheng. Basically, that if you have anomaly polynomial of that type, you gauge 2 out of 3 of the symmetry, the other one become non-invertible.
Yeah.
So that's the idea. So it doesn't have to be always.
That's an example, yeah.
Yeah, but that's a prototypical thing. Yeah. We did this extensively in ABJ type theory, basically.
But
I mean, I think gauging outers is okay, that's, yeah. All right. I think it's slightly different, because in that case you're gauging the NSO charge conjugation doesn't act non-trivially. It's a normal subgroup, right? So whereas and the non-invertibility came because of the anomaly, whereas the cases I was suggesting are slightly different. It's when the non-invertibility is not becoming because of the anomaly, but because the subgroup you're gauging is not normal.
Right.
So I think they're kind of distinct, actually.
I see. That's a good thing. Yeah, I haven't worked on that so far. This is something to look at.
Yeah,
Okay.
it's known as the intrinsic and non-intrinsic thing, I think.
Well, no, they're both both of those things are not intrinsic, because they're both coming from gauging.
Okay, I see. Okay.
What's the difference between this intrinsic and non-intrinsic?
Well, very roughly, if it's not intrinsic if you can get the non-invertible symmetry by starting with a theory that has a regular invertible symmetry, maybe with a Tufte-anomaly, engaging a discrete subgroup, or maybe a discrete sub-2 group or something like that. So you can always, in other words, you can always relate it to something non-invertible by doing a kind of topological operation like gauging a discrete symmetry. Whereas there could be non-invertible symmetries that are not like that, where they're just so intrinsically non-invertible you can't get rid of it by gauging a discrete thing.
I see.
Okay, do we have more questions for Marcus? So I'd say let's thank him again. And we can stop the recording.